Hello everyone, and thank you for joining our webinar today on power integrity and noise immunity. My name is Mohamed Al-Alami. I'm a senior field applications engineer for Würth Electronics. I've been with the company for coming up to 6 years now. Prior to that, I worked in the aerospace industry doing power supply design and development as well as EMC testing. Before we start, I would like to extend my thanks to Rohde and Schwarz for giving us the opportunity to present to you today. I would also like to mention to you as well that we have got a second session on EMI shielding solutions later on. So please join us for that at your convenience. Thank you. Today's agenda, we're planning to start off by talking about identifying the different types of noise, and then we will move into more of a practical approach to this webinar. We will be looking at the boost converter, identifying its noise sources, and looking at a particularly badly designed converter circuit, identify those bad design practices, and look also into naturally improving this design and how we can do this through either components, layout and tracking, various different techniques we will look into, and we will finish off with all of these being implemented in a good design practice. I would say most people are familiar with the different types of noise, common mode and differential mode, in other words. So a differential mode, this is just a quick overview and a reminder. So a differential mode current is naturally the current that is responsible for delivering your power to your load. So that's the current part is fairly clear, I guess. On the schematic, you can clearly see where those currents are flowing. It's easier to identify where the noise is coming from, switching, clock frequencies, data rates, and so on. Usually it's high currents and high di by dt's, high dv by dt signals. And it's not always the case, but they result into conducted emissions, EMI problems, but of course this can be also irradiated as well. From a common mode point of view, this is where it becomes quite challenging because the current paths aren't clear. Sometimes the current goes through huge loops in order to, from a common mode point of view. They're relatively low amplitude currents, so microamps. We're not talking about here amps of current. And more likely than not, it results in radiated EMI problems. But we've also seen it in conducted as well. So just to show you as well how this actually works when it comes to actually performing the testing. So you've got your unit, which is your noise source on the right hand side, which is usually connected to a LISN, a line impedance stabilization network. And what we're looking at is the plus, the positive, the negative, the live and the neutral, and the ground or earth. And on these lines here, we will see both differential and common mode noise being conducted on these lines. So there's no separation between those. You will see a combination of this type of noise. As you can see quite simply, the differential mode is going from the plus, coming back through the minus. With the common mode, goes on the plus and the minus and comes back through the ground, hence the large loops that we were talking about before. And identifying where those loops are, identifying where those parasitic components that are providing this pathway for those high frequency noise currents to flow through. That's also the other challenge in order to identify where you need to introduce your solutions or minimize those loops from a layout tracking point of view as well. So cut a long story short, LISNs, when you're coming to test, you're looking at both common and differential combined together. So one of the purposes of today is to make life a little easier by introducing this. Let me just use my pointer, my laser pointer. Oh, this is now a dual LISN. So it's something that we have actually designed between ourselves and Rohde and Schwarz. You will see this later on when we're looking at some of the testing that we have done on this boost converter. So this dual LISN has got two RF outputs which are combined using mini circuits, splitter combiner modules. So in this case, of course, you'll be introducing a 3 dB attenuation for the combination of the two. But what this does, what the advantage of this is it gives us the output as a common mode or a differential mode, so we can see both common mode and such noise as well as differential mode noise coming out of our DUT. And we can see this on the spectrum analyzer or the oscilloscope. In our case, we have used the RTO 2014 oscilloscope with the FFT function to view this. Again, as I say, you will see this later on when we come to do some of the testing. So looking now at the boost converter, moving into the practical side of things, let's identify first the noise sources, the areas which are carrying high dV by dt on a boost topology. So what we see here is the schematic for the boost converter, and as highlighted, we have got a high dV by dt node. So this is a critical node that we need to keep in mind when it comes to layout and tracking, because this node, which we call a hot node, is also another name for it, will be causing quite a substantial amount of noise. The harmonic content of that voltage signal is quite high. The other area that we need to also be mindful of is the high di by dt, the critical current loop. As you can see, this is the critical current loop where you see a high di by dt signal flowing through this particular loop. So this needs to be, in other words, minimized from a size point of view to limit its ability to radiate and cause issues. Another aspect of the boost, which is applicable really to all types of converter topologies, all types of circuits that you design, is looking at the parasitic model. Now, a parasitic model is very important because it's these parasitic components, these undesirable effects, that do cause us the grief, that do give us the headache. A boost converter or a buck usually switches at a fixed frequency. So you're quite clear on what you're switching at: 500 kilohertz, 1 megahertz, and so on. Unfortunately, it's these parasitics that we have in that model that result in much higher frequencies being introduced, much higher noise, like we say, sometimes being introduced on those lines, input or output. And this is where it is critical for us to try to minimize the impact of these parasitics. In some occasions, you can't do anything about it because this is part and parcel of the actual component that is being used, but as you will see later on today, there is an opportunity for you to select a better type of component sometimes, which will give you a lesser of a parasitic effect. So what are these parasitic issues that we can see? A simple capacitor, for example, we can start off with. Capacitor ideally is just a capacitor, but realistically you've got an equivalent series inductance and an equivalent series resistance. These parasitics could be the wiring of the inductance and the resistance, of the wiring, the cabling, the actual tracking within the PCB itself will have a certain inductance and a certain resistance. The output capacitance of the MOSFET, the same thing for the diode, the junction capacitance of the diode, and from an inductor's point of view, of course, interwinding capacitance as well as the series RDC resistance. All of these parasitic effects combined together will result in higher frequency ringing and noise coming through. And you will see this later on as we look at some of the time domain measurements that we have done for this converter circuit. All right, so next we will have a look at this practical example, and this will show us we will introduce to you the bad design practice in that example. So a circuit diagram, just to give you a brief spec requirements for this design. We have an input voltage of 9 volts coming in. The output is set for 12 volts. It's a 15 watt power throughput. The switching frequency of the chipset is around 650 kilohertz, and it's a current mode control topology. The idea behind this is it's non-synchronous, so you've just got a standard diode rectifier at the output. We've identified on the schematic the critical loop that we've talked about before from a di by dt point of view. Naturally, the hot node is there. That's quite clear. I'll just draw your attention to a couple of things as we look at the schematic, just to identify maybe some of the things that may come out straight in terms of an issue. one, or let's say a bad design practice. The use of aluminium electrolytic capacitors on the input and the output without any other type of capacitor also being present. So that's an initial point to keep in the back of the mind. We will talk about capacitors in quite a bit more detail as we go through later on, but this is not necessarily the best design practice that we should be implementing. Another point which you may not be familiar with is the use of this PD2 series. The PD2 series of inductors is an unshielded type inductor. So we have got a whole set of webinars that talks about inductor selection, Red Expert, difference between shielded and unshielded inductors, and where the advantages and disadvantages lie. But with this, PD2 is an unshielded inductor, so from a pure PMI point of view, that is considered as a slight disadvantage as well. So you can always replace this with a shielded inductor. That's also an option there. But that's as far as what we can see here. One aspect will become a lot clearer. Further aspects of the bad design practice will become clear, I should say, on the following slides when we start looking into a bit more detail at the layout and tracking. So here we go. There is the layout and the tracking. So that's the two main aspects: component selection when it comes to improving a design. So we're looking for more optimal type components to reduce the noise. We're looking at much better or much improved layout and tracking. And between those two, you can get rid of quite a large volume of your EMI problems. The final aspect to consider is the introduction of filtering as well. Now, that is good design practice, as you will see by the end of today, or by the end of this session, I should say, the introduction or the inclusion of filtering as part and parcel of any design. As opposed to as a reaction to a failure of an EMI test. So in here what we see is quite a wide range of issues that have been not designed in or considered bad design practices. So we've got a single ground plane. We haven't created a small enough loop. So the loops, the di by dt loop is relatively large. Going through, there is the resistor and there's the output capacitor here. So we are talking about making a big mess of it. But that was the intention. So the intention was to try to make this as bad as we can make it, in a sense. So you can consider that maybe some younger people, some of the engineers, the design engineers, do not necessarily have the experience on how to lay out and track and how to minimize these loops and how to look into the EMI aspect of laying and placing a power supply. So sometimes you end up with a less than desirable, let's say, layout and tracking practice. So that's one aspect in here. So we have a single ground. We recommend usually having an analog and a power ground, separate ones. The track for the sense resistor, that's an absolute no-no there. So that's a very sensitive signal. That should never be run on or jumped from one layer to another and run underneath particularly noisy tracks and components for the gate source signal, driving the gate of the FET, which is coming through here. So there are quite a few of these things that are these practices that haven't been implemented appropriately on this design. Another thing is the feedback signal as well. So that's coming from the diode. Naturally, you're better off, and that recommendation is always to take it off the capacitor straight into your voltage divider, into your IC, to feedback the output voltage. So a few different aspects and issues. If you look more closely into this as well, you'll see some key capacitors or decoupling capacitors have been left quite a distance away from the actual IC, where they actually need to be as close as possible to the IC itself. So okay, that covers the bad design example. Now let's see how we actually set up to do the measurements. So we did two types of measurements for this testing. So we have looked at setting up time domain measurements, and for that we used the RTO 2014 Rohde and Schwarz oscilloscope. It's a fantastic piece of kit. It's a 1 gigahertz bandwidth and 10 G samples per second, and a 4-channel oscilloscope. And this oscilloscope is actually also capable of giving you some really good frequency domain FFT plots for these signals, which we will also see in a little bit as well. We will also show the option of looking at some of the EMI test results using an EMI receiver later on as well today. So with this, the setup is fairly straightforward. What we have here is just a power supply supplying the input of the boost converter, which is what you see on this side here. And this is loaded with a rheostat load, or variable rheostatic load, rheostat resistive load on the output. Next, we will have a look at the scary time domain measurements for the ripple on the input and the ripple on the output. So starting off with the output voltage ripple, and this is, remember, without any filtering. All this circuit had was just those 417 microfarad aluminium electrolytic capacitors on the input and the output. And it's horrific. It's horrific. Yeah, the ripple voltage on the output is 12.2 volts peak to peak. This is very high frequency noise that you can see here. This is not the frequency naturally of the switching of the power supply at 60 to 30 kilohertz, but of course it's a much higher ringing frequency, partly because of the parasitics within the circuit, and much bigger part as well because of the bad layout and the tracking of the board. And of course the limitations of the components. So all these different aspects of bad design practice combined together can give us a really bad picture, like what we've seen in front of us here. And the same is applicable, of course, on the input side of things, and we can see here quite clearly that we've got a substantial amount of ripple on the input side. So the design is not great, unfortunately, but this is a good opportunity for us to take this and see how we can improve it step by step. And that is the purpose behind today's webinar. Another purpose as well, and the reason why I have tried to also include time domain measurements, is just to put across that with a very decent oscilloscope and a really good voltage current probe, you are able to debug a lot of your EMC or EMI issues using the oscilloscope. You don't necessarily need to go and test into a test house. You don't necessarily need to also have a receiver, an EMI or spectrum analyzer. You can, with something like this RTO 2014 that we've used, either in an FFT mode or even time domain mode, as you can see here, identify some of those issues and some of those frequencies that you have got an issue with, and accordingly introduce suitable solutions well before you go into the EMI test lab. Okay, so that was the time domain measurements. Let's look at the frequency domain measurements using that EMI receiver. We used actually the, what was it that we used at the time? Oh, the ESRP EMI test receiver, also from Rohde and Schwarz. Another fantastic piece of kit. So for that, the setup was using that dual listen I mentioned to you before. So the dual listen, you can see it has got two RF outputs, and with those mini circuits that we've mentioned before, the power splitters and combiners, we could look at common mode and differential mode also separately. But what we have got here is the unit, of course, the input connected through the listen and onto the boost converter connected across to that rheostat load. Same setup, but of course with the listen setup on the front end and using the ESRP receiver. And here we go. This is the result. So that's the EMI output from our unit on the output side of things and on the input side of things. So what we can see here is we have got quite a large fundamental at the 630 kilohertz, the switching frequency of the power supply, and its harmonics all the way through. You will note that we have decided to test this up to 100 megahertz just to give us an indication of what might be happening in the radiated emission side of things. Naturally, of course, a pinch of salt, we're not going to get an accurate measurement there, but it just gives us an idea as to whether we're going to have any issues further up the frequency spectrum. So what we decided to do is look at how much attenuation we need to introduce as part and parcel, or to try to attenuate the highest peak that we have got at 630 kilohertz. So 80 dBs is the marker amplitude max peak, and if we look at worst case scenario, let's say this is the average, we need to bring it down to the 46 dB level or value, and that gives us 34 dBs of attenuation. And what we will want to do is have an extra 10 dBs of margin, just to be on the safe side, giving us sort of an overall 44 dB of insertion loss or attenuation at that 630 kilohertz fundamental frequency. So we can clearly see on this plot that main issue that we're seeing here is the switching frequency of the power supply. As we go up in frequency, we will also see that there's going to be quite a substantial component of those high frequency ringing that we saw earlier in the time domain signals. Now, I know some of this could be very much associated with the scope measuring and the scope itself and the way you're measuring on the board, it's on the PCB. Hence why I mentioned it's very important to get a decent scope when you're doing these measurements, if you're going to get a more realistic reflection of what's actually happening on the board, as opposed to it being pickup, or noise pickup. And that's where I think investing in a decent set of scope probes would be very useful in this case, because it also gives you that better understanding of what's going on on your system, on your board. And this is also another interesting result. So the previous results that we have seen were using the ESRP, EMI receiver. What we've decided also to do is use that RTO oscilloscope, and we have, it's got a very nice function called a spectrogram function. Part of using an FFT as well, and using those power splitter and combiner boards, we were able to look at the noise content of the input signal. In this case, we're just looking at the input side of things, differential and common mode. So we've concentrated on the input side, naturally, and we've looked at the differential and the common mode content of that signal. So we've split that up using those splitters, and it shows us that there's quite a substantial amount of 630 kilohertz and its fundamentals of noise. But there's also common mode, and the common mode is coming up further up in the frequency spectrum. So this is the other area that we need to concentrate on as well. So this is where it gives you that extra bit of visibility, and using a decent piece of equipment will give you that information ahead of you going into any form of even de-risk testing at an EMC test lab. All right, so we have looked through all of the bad design practice examples and the issues that we were seeing there. And now we're looking at improving this design. Where did we fail? What were the weaknesses? I guess it was quite clear from a layout and tracking that was one main weakness. I did also allude to the caps. I also alluded to filtering. So let's have a look at what we can do with this design in order to improve it. So I'll start off with the capacitor side of things. So I said capacitor that we were using is not necessarily the best type of capacitor. So we're looking at now selection of different types of capacitors. Before we actually look into this design that we've been looking at so far, let's just have a look at general capacitors, their behavior, what types we have around us, and what should really be the criteria for selecting a suitable capacitor for this type of application. Different capacitors are useful for different types of applications. So one thing to keep in the back of the mind is a big difference between an ideal capacitor and a real capacitor. So I mentioned it earlier, the real capacitor has got an equivalent series inductance, equivalent series resistance. It's never just the capacitor by itself. And it is these, what we called before, parasitics, that limit the performance of the capacitor. And that can result in the noise that we have seen in the time domain or even in the frequency domain on the earlier slides. So these are very key parameters, ESR in particular. The curve of the impedance of the capacitor shows that yes, it will give me a capacitive reactance for a while until a certain type of frequency where it will no longer give me a reactive capacitance anymore. It will become more an inductive reactance, sorry, I should say. So that's very important to understand the different types of capacitors that are available and how they can impact the performance of this capacitor in something like a boost or a buck converter topology. And that's associated with ripple current. So that's also another important parameter to keep in the back of the mind, is the capability of handling ripple current. Aluminium electrolytics are not the best when it comes to handling high ripple current. They can't. They are very limited in terms of how much current they can take through them. Their ESR is relatively high, which we will see again on the following slides. Ceramic capacitors are fantastic. They have got the lowest ESR. But so does that mean either aluminium electrolytic or ceramic? Is there something in between? Yes, there's something called a polymer capacitor. So we will talk about polymers next on the following slide. Polymers tend to bridge that gap between ceramics and aluminium electrolytics. Okay, here we go. So polymer versus aluminium electrolytic. So the aluminium electrolytic has a higher voltage rating. So if you've got 400 volts, I'm sorry, can't do much about that. So that's where, yeah, aluminium electrolytic will beat the polymers hands down. Naturally, from a price point of view, it is cheaper for the same capacity and voltage rating. But the polymers, and especially when we're talking about the standard type of converter topologies with the standard levels of voltage and current, the polymers are absolutely fantastic. Fairly small ESR compared to aluminium electrolytic, and you still pack quite a punch, so they can get you quite a high level of capacitance for that. The main issue that they have is the amount of voltage, the blocking voltage, the rated voltage that they have. That's the only thing that they are limited on. But from an ESR point of view, naturally ripple, they're two sides to the same coin really. Drying out issues, life, they are a hell of a lot better polymers are than aluminium electrolytics. I have got, by the way, a totally separate presentation that talks in a lot more detail about capacitors, the calculations of the required capacitance for a DC-DC converter on the input, on the output, to account for the ripple requirements, for the transient load and line requirements, and so on. So this is just a quick snapshot, just to give us an idea of what we're looking for when we are selecting a capacitor. I mentioned life. The life of a polymer is considerably higher than that of an aluminium electrolytic. So if you can afford to use a polymer, then I would say it's a no-brainer. It's definitely a much better technology, a more reliable technology than aluminium electrolytic. So where is the issue with using MLCCs? They're fantastic. You said to us it's fairly low ESR, so why do I need to go across to polymers? Everything has its place in a power supply, or in general in electronics design, I should say. So, and I'm not saying that MLCCs do not have a place. They absolutely do. They're fantastic components. However, they will also have limitations. And one thing to keep in the back of the mind when it comes to MLCC is their voltage dependence. That's something that a lot of people do not necessarily account or take into account when they're designing. They just look at it at a fairly small 0402 part. Oh, I can do 50 volts now, fantastic. But you don't know how much capacitance you've lost so by the time you've done 50 volts at 0402. So that's something to keep in the back of the mind. And this is one thing that I have to say with Wurth, we're really great at. We give you all of this information, and we give it to you so easily. You can find it in the click of a finger on our website. I'll show you on the next few slides. But this is something that's very important, the DC voltage bias impact on MLCCs. So keep that in the back of the mind. And just to give you some actual example of something that we have done is we've compared several MLCCs stacked in order to give us an amount of capacitance. And in this case, the chipset that was used was 0805 at 6 volts. These components stacked in parallel would give us 216 microfarads. Due to the DC bias, there are 47 mics each, and there's 24 of them. So I'm supposedly getting 1.1 millifarads there. I only get 216 microfarads, and that's due to the DC bias. And you're taking up quite a substantial area still with that. While if you use a horizontal chip, and this is a really nice new also technology that we have recently introduced. When I say recently, it's more than a couple of years now. And the horizontal chip polymers, they have no DC bias effect. So it's a 6.3. You can put 6 volts across it and still get 220 microfarads. And the footprint is 44, from an area point of view, 44 millimeters squared, so considerably smaller. There is still a place for polymers. I'm absolutely convinced that they are the better technology. Sometimes it's just about the cost, but for me that's false economy, because you are using more area. And given the issues that we've recently had with sourcing MLCCs just a couple of years ago, where everything was on allocation and you couldn't get them, they were like gold dust, I think it would make sense to combine. I wouldn't say just use one technology. My own experience in the past, I have used both polymer, wet gel tantalums in my day, as well as MLCCs. The wet gel tans were full bulk. I couldn't use at the time H-chip polymers. It was not allowed in our industry. But wet gel tantalums as well as these. I would say solid tans are an absolute no-no. I know people love these. They think they're getting a good deal out of fairly high capacitance, fairly small size. They very much look like this H-chip aluminium polymer, but it's an absolute false economy. If you think the MLCCs are bad, I mean, these are the absolute bottom of the pile, these solid tans, from every point of view. And I don't want to diverge too much into talking about those, but my experience with tantalums is absolutely no. So I've included in here on the next 2 slides a couple of examples from our component selection tool called RedExpert. It's available on our website. Please go and click the link and have a look. This is just to give you that indication of the drop in capacitance as a result of DC bias, and to show you how RedExpert makes it so easy for you to figure that information out. We've got the curves for it. We include the actual data in a column in the table for it. You can compare different sizes. You can compare different voltage ratings. So it's really nice and simple way of optimizing the selection of your MLCC. From a polymer point of view, again, the idea here behind this is to show you can get quite a large capacitance for a very similar footprint to what you would be getting from the MLCCs we've just looked at earlier. So again, there's not necessarily a good economy by using MLCCs. There is room for polymers. They do give you substantially high capacitance. They do pack quite a substantial ripple current capability. So there is still a positive for our polymers. And to finish off with, I'll just mention that we have got LTSpice models for all of our capacitors available. And this will help you model, simulate these designs and get a very accurate estimation of the behavior of these components. These are really accurate models that we have got for generally all of our components. But of course, we're talking capacitors here. Now, let's go back and look into our specific design example, our bad design example, and see how we can improve that bad design example from a selection of different capacitors point of view. And what we're going to concentrate on at this point in time is just looking at the different input capacitors. So what we have done here is we've looked at selecting a polymer, an aluminium polymer, 10 microfarad. So that's a substantial drop. We had 470, if you remember before, at the input and at the output. Now we're changing all of that. We're saying, all right, we're going to go for a 10 mic so I can compare apples with apples. That was the idea. That was the purpose. So we're going to look at a 10 microfarad aluminium electrolytic versus a 10 microfarad polymer. And on the next slide, you'll see a 10 microfarad MLCC. But let's just look at these two to begin with. And just to consolidate the point, you can clearly see that the aluminium polymer, which is the blue colored part and the blue colored curves, outperforms by a mile the aluminium electrolytic from an ESR point of view, from an impedance point of view. It's substantially better in terms of performance and capability. Ripple current, you can't compare the two. So again, from and even from a size point of view, you can see they're pretty much the same in terms of size. And this series here, the PSLP, is a low profile, so fairly low in terms of height, 5.8 millimeters. We can't discount MLCCs, and as I say before, MLCCs do have a place, but for me the MLCCs are there to complement. I can still get a substantially high level of bulk capacitance from a polymer, and I can add some extra MLCCs to give me the higher frequency rejection capability at a lower value of capacitance. But again, in this case, we are comparing apples with apples. So this is 10 microfarads, it's an X7R component. And what we have done as well is put all three of them together in terms of an ESR curve, and we can see that, wow, MLCC beats even the polymer hands down when it comes to ESR. So why are you saying, Mo, that you have to use a polymer? Not necessarily the case. You can always use an MLCC. Watch out though, that MLCC's dropped its capacitance quite substantially. So its capability as a capacitor at 10 microfarads to reduce your ripple has now been degraded by 25%. Okay, that's not going to be the case for my polymer. And the acid test is when you come to test. So let's have a test. Here we go. So what we have done on here is we have replaced those 470 microfarad capacitors with a 10 microfarad aluminium electrolytic first, then we've put in a polymer, and then we've put in the MLCCs that you've seen on the previous couple of slides. With the aluminium electrolytic, again, it's horrendous. The ripple is quite substantial, 974 millivolts peak to peak. Its ESR is fairly high, 1.45 ohms. So that ESR is shaping that ripple. The capacitor is doing nothing, basically, from a ripple point of view. The polymer, though, at the same natural capacitance value, much lower, 20 milliohms of ESR, ripple voltage, beg your pardon, 281 millivolts peak to peak, and that's here also we can see the high frequency ringing noise as well. So that's still here. It's just you can't see it because of the larger ripple associated with the ESR. That's taken over this, so that's basically doing this. So this is swamped this high frequency noise. And when we come to look at the MLCC, which on paper looks like it should really be substantially better than polymer, 2 milliohms as opposed to 20, but when it comes to the reality of actual ripple voltage, it's not that far. And the reason for that is what I alluded to earlier, and that was the DC bias impact, the DC bias effect. So you are not necessarily always getting the most out of your MLCC. Okay, so we can do all of this and do all of these measurements and start taking components on and off the board. But I said before, we do have models and we can always use LTSpice. And in LTSpice, we can simulate the impact of the parasitics of the capacitor in terms of its ESL, ESR, and the capacitance itself. and look at how much ripple is attributed to each one of these parasitics. This is a really nice exercise, but unfortunately this will take us to the next level of simulation and testing, but that's not for today, that's for another day. We can also use LTSpice to look at each one of these three voltages that we've seen before and look at its noise content, harmonic content of those signals as well, and plot these in LTSpice just to see which one is giving me the highest level of noise that I need to worry about, which is the key factor, which is the weakest link, I guess, in this setup. All right, so that's capacitors done. So the next step is to look into filtering, and that is another area that will improve design quite substantially. So from a filtering point of view, what we have done in this case is used the same bad design practice as it stood, with its 470 microfarad aluminium electrolytic capacitors, and we have introduced an LC differential mode filter as well as a common mode inductor on both the output as well as the input. And just to also show you, starting off with the differential side of things, the DM mode, LC input and output filters, we've used LTSpice. Now I've mentioned before we have got models in LTSpice for both capacitors as well as inductors as well as common mode chokes. Everything's there. And we've tried to compare here an ideal LC with an actual component, an LQS, and an aluminium electrolytic again. And here is a higher value of inductance with the same aluminium electrolytic capacitor at 10 microfarads. And we're looking here at the amount of attenuation that the filter will give me at that 630 kilohertz fundamental. Now, if you remember, going back earlier, we've mentioned that we need around 44 dBs worth of attenuation. Now, the ideal filter will give me quite a nice level of insertion losses, around 40 dBs or so. But as we go through the more realistic components, we see that that attenuation drops quite substantially. And the reason for that is that ESR, that 1.45 ohms that we saw earlier, dampens that and reduces the effectiveness of my filter capacitor. And this is why we went from 10 microfarads to 15 microfarads. That's where you go from red to blue in order to increase the amount of attenuation to get me around the 30 dB marker of insertion loss at 630 kilohertz. Now, that's not necessarily the best of solutions. We have gone with this at the time, but there is also, of course, the opportunity to introduce either an MLCC here or to introduce a polymer there if we need a fairly high value of capacitance in order to improve things. I would be less reluctant to start increasing inductance because of the current side of things. That becomes more lossy, that becomes more hot. So it's easier to play, especially when we've got smaller values of capacitance, to play with capacitance and smaller voltages, I should say, to change capacitance value than it is to change inductor values, especially when the current is relatively high. So keep that in the back of the mind. This is the board showing you the LC filters on both the input and the output side of things. I've also included on this slide a link to our website. We have got lots of evaluation boards that can be used for our customers. So please let the regional sales manager looking after your account know if you need any of these boards to help you with developing filters for your designs. We're more than happy to support you with this. We have got differential, common mode, low voltage, mains voltage, all the various different types of eval boards available. One thing to take care of before I leave differential mode side of things is when you're introducing an LC filter on the input side of a power supply, you have to be very careful because this can cause an instability as a result of the negative impedance that the DC-DC regulator presents to the output of the filter. So a DC-DC regulator is a constant power load. So that introduces a negative Z for the oscillator, for the LC filter, sorry, which means that it can oscillate, as you can see here, if it is not appropriately damped. So that damping of the aluminium electrolytic is sometimes a good thing to have as well. So there is a whole other set of presentations that I've done that look at this in a bit more detail and look at how we can calculate the damping requirements and how we can design the filter so that we avoid any issues with instability. But that's for another day. Okay, so that covers differential. Now let's look at common mode at the input and at the output. Now, if you remember back to some of the test results that we have obtained through the RTO or the EMI receiver, we have seen some fairly high frequency common mode noise, both at the conducted emission 630 kilohertz and its harmonics, as well as beyond the 30 megahertz into the radiated emission side of things. And that's one of the reasons why we have looked at introducing two different types of common mode chokes. What you see on the left hand side is a common mode choke that is made of a material called nanocrystalline. And this is a fantastic type of material because it has got a relatively wide range of insertion loss. So it's a wide bandwidth type material, and it gives me quite a substantial amount of attenuation, particularly at the 630 kilohertz, so in this case about 15 to 20 dBs of attenuation. While further up in the spectrum, as we go beyond into the radiated and further from that, that material is relatively limited in what it can provide, and hence why we use this other type of component, which is we call it an SL5. This is a nickel zinc based material, and this one gives us quite a substantial amount of attenuation into the radiated emissions, and it goes up all the way to around the gigahertz marker. So this way we have covered that entire spectrum of common mode type noise that we've seen before. That is it. That's the full filter there. So on the input and on the output side, so we've got the LC differential and we've got the common mode stage for both the input and the output side. And here we go. There's the acid test. That's what we get when we introduce this filtering on the input and on the output. Now, remember, this is two filters, a differential mode and a common mode on both the input side and the output side. And what we see here is on the output, we have dropped the amount of ripple from 12.2 volts peak to peak to 162 millivolts peak to peak. And on the input side, that dropped from 411 millivolts peak to peak down to 51 millivolts peak to peak. So a substantial improvement. However, we still don't know if this is going to be enough or not. Is this going to make us pass our EMI, or do we need to take it to the next level? Now, for me, this is a good type of solution because sometimes you are limited in what you can do in terms of introducing solutions for your design. Sometimes you are having to just change capacitor values. So you have looked at before how you can introduce a bit at a time in terms of solutions. Sometimes you're able to or happy to just introduce filter, respin the PCB, just do the filters by themselves. But sometimes you're a bit greedy like me and you want to do the whole hog, you want to do the whole thing. And that's what we look at on the next slide, which looks at the good design practice example to finish us off, to take us home. So, and this look now at introducing a whole raft of modifications to the design. Let's just start off by explaining what we have done here. We've kept the common modes the same as what we've seen earlier. The capacitor and the inductor that we have used, the LC filter, stays exactly the same. What we have also done here is taken out that 470 microfarad aluminium electrolytic, and we have replaced it with a polymer 180 mic polymer capacitor, as well in parallel with an MLCC 10 microfarads. And for me, this is the practice to use or to do in a power supply, a polymer and an MLCC. One other thing that we have also changed, if you remember back to me saying that we were using in a bad design practice, we were using an unshielded inductor. We have introduced a wee LHMI. The LHMI is a fully molded shielded type inductor. So that's also another modification or change that we have done. So that's the component side of changes. What have we done from a layout and tracking point of view? Where, hey, now that's an undistinguishable board from what we've seen before. So in here, we have minimized those critical loops. We have ensured that our high di by dt hot node is isolated, so it's nicely coupled down to the ground. There's nothing that can cause any coupling onto sensitive signals. The feedback signal is coming directly from the output of the capacitor, as you can see, straight into our control circuit. We have got two separate grounds plugged together at a single point. This is all good design practice in terms of trying to minimize loops, isolate different grounds, and look into where sensitive signals are. Make sure that these sensitive signals have got a minimum pathway for them to run through, as well as, of course, making the capacitors associated with the component, with the IC in particular, the decoupling capacitors, I should say, in very close proximity to the actual component itself. So you minimize any noise or glitches coming onto the sensitive signals. That's very key, and this is another major change that we have done in this. So you can see we have implemented pretty much everything that we have talked about before, 1, 2, and 3. So capacitors or component modifications, LC and filtering, in terms of filtering, and layout and tracking. And this is just to show you the good design practice. So this is that board, but without any filtering. So that's minus the LC filter and minus the common mode chokes. And we have dropped down on the output to 2.3 volts peak to peak, and on the input to 197 millivolts peak to peak. And that's between brackets, by the way, that's comparing to the bad design practice. So basically, this is just attributed here to the change of that capacitor and the change of the inductor. Plus, of course, all of the good stuff that has happened from a layout and tracking point of view. But again, this is without any filtering. Now let's have a look. Oops, I've still got a failure here. I've still got a failure there. So I'm still not there, unfortunately, even with the good design practice. Now let's have a look when we introduce our filtering, the common mode chokes and the differential. And here we go. Now we're down to 47 millivolts and 10 millivolts peak to peak on both the output and the input. And if we look at the spectrum, it's scarily quiet. So, eerily quiet, I should say. That's the better expression. So there's nothing going through there, common or differential. So it's all been quashed quite substantially and reduced to naturally a very clear pass level. This is something that can be done quite easily, I guess, without you, as you can clearly see, without you even having gone into any lab, with a good piece of equipment and that time domain or frequency domain. You can have a look at this and try to use this in order to preempt any potential issues and plug any problems in the bud from an early stage before you have gone to EMC testing. And we've done the same test with that splitter to show us both differential and common mode noise using the RTO 2014. So to finish off, I've just got a couple of slides just to show our Würth Electronics presence is global. So wherever you are joining us today, you will have somebody that will be able to support you. We have got sales offices all around the world. And what I've also included on the next slide is a link down at the very bottom to our Contact Us webpage. So on here, I've left the UK contact details in terms of our UK office, but you can easily enter any country here, and it will also give you the contact details, email address, phone number, and so on, as well as the address of the Würth office that looks after you. So please do not hesitate to use and abuse us. Let us know if you need any further support or any help. We're more than happy to support you on this. Thank you so very much for your attention. I hope you have enjoyed this session, and hopefully look forward to seeing you in the future sessions. And if you have got any questions, please fire away. We're here to help. Thank you.